Hi, this lecture continues our investigation on projectiles, and this time we're going to be looking at projectiles that are shot at an angle, or angled projectiles. Our objectives in this lesson is to determine the initial variables for the x and y axis, in particular the initial velocity. In this case, my horizontal velocity and vertical velocity will neither of those velocities will be zero. We'll also look at some of the symmetry and what happens with air resistance here. So first off, angled projectiles have the same projectile requirements as horizontal projectiles. We're still going to be ignoring air resistance, and gravity is still going to act on the projectile at 9.8 meters per second squared downwards. Okay, and again, we focus on the projectile after it's launched and before it is caught. Frequently, we'll be looking at situations where the projectile is fired on level ground. What this means is that the projectile starts and ends at the exact same height, or my displacement for the entire path of the projectile is going to be zero on the y-axis. The generalized problem is going to have a difference in the starting and ending height. Okay, the generalized problem is the more general situation. So the horizontal projectile is just a subset of the angled projectile with the angle set to 0 degrees and an initial height. Okay, in this case, and in the angled projectile case, it's always important to pay attention to the height and the positives or negative directions, because those are going to be represented in the positive or negative signs in your variables. So here's an example, okay? I have a projectile, it's launched at an angle of 25 degrees and an initial speed of 16 meters per second. What is the projectile's range? Okay, first off, if you've never heard the term range, okay, it's basically the horizontal displacement, or the x displacement of the projectile when it lands, okay, or just before it lands. The initial velocity, if you'll notice, okay, at an angle of 25 degrees and initial speed of 16 meters per second. That's magnitude angle format. Again, we really don't work in that format, though we write in that format and we understand it. But we need to convert that into its horizontal and vertical components, because those are the values that we need to stick into our kinematic value tables. So that initial velocity has x and y components, or I hat j hat components, and we can convert that using our sines and cosines. The x component is going to be the magnitude of that initial velocity times the cosine of 25, and the y component is going to be the magnitude times the sine of 25. Okay, the magnitude is 16, so when I plug all those things into my calculator, tells me that my x-axis initial velocity is 14.5 and my y-axis initial velocity is 6.76. Assuming up and right are both positive directions like a standard coordinate system, I can express my initial velocity in component form as 14.5 meters per second I hat plus 6.76 meters per second j hat. So I'm going to rewrite this, okay? When I'm asking what is the projectile's range given those initial parameters, what I'm really saying is that I have two kinematic problems, okay? One moves at a constant velocity horizontally at that 14.5 meters per second. At the same time, a ball is going to be thrown upwards at 6.76 meters per second. So I have these two kinematic problems, one constant velocity, one free fall. Yes, it was thrown upwards, but it's still a free fall. Okay, and then the question is really asking, where is the horizontal ball when the vertical ball gets back to where it started? So let's look at that kinematic equation table, okay, x-axis and y-axis. Just like with the horizontal projectiles, okay, we're going to separate those two and just treat them as two one-dimensional kinematic problems. Okay, one's constant velocity, the other is a free fall problem. Okay, the only thing different is that my y initial velocity is not going to be 0 this time. It has a value that we calculated using components. Okay, and whenever you fill it out, okay, make sure you know what the positive and negative direction is. If you're ever unsure, just go with the standard, okay? Up is positive, right is positive. anything that's negative or in the negative direction, make sure it has that negative sign. So here's my projectile table. Notice I have on the left side the y-axis, that's my free fall, and the x-axis is constant velocity. I filled in the initial velocity on the y-axis, the 6.76, and the 14.5 on the x-axis. Notice I don't really have a final velocity or an initial velocity on the x-axis because it is constant velocity. I'm only going to have 4 variables on that side. Okay, don't write both of them. My accelerations are there. On the x-axis, 0, that's why it's constant velocity. On the y-axis, I have 9.8, and notice I put the minus sign in there. Okay, so it's minus 9.8, or 9.8 downwards is the negative direction. Okay, I also have one more value in there. Okay, I also have the 0 meters per second. Okay, this value right here, and where did that come from? Okay, remember at the beginning I said level ground, which means my displacement in the y direction is 0 meters. Okay, so therefore, as long as I'm looking for the where it returns to its same level, my displacement is going to be 0. Well, the same rule applies whichever axis or whichever problem. I have 3 variables. Let's start with that one. Okay, so the x-axis only has 2, the y-axis has 3. So let's try and find out when or at what time does my free fall ball get back to its same height. Okay, so first off, we do the displacement is equal to VIT plus 1/2 AT squared. Stick in the numbers from the y-axis and solve for time. Notice because I have that displacement equal to 0, I can actually eliminate one of the time variables. Okay, so this t cancels out with the squared. So I'm left with just 4.9 t, after I move it to the other side, is going to equal 6.76 meters per second. And if I cancel my units, okay, the meters on this side cancels with this, and the s squared, when I multiply out, will cancel one of these, and I'm going to be left with time of just 1.38 seconds. I take that 1.38 seconds now, and I just bring it over to the x side, and I substitute that for the time. Okay. In this case, I don't have an acceleration, so I can ignore this and plug in my numbers, and I find out my displacement is about 20.0 meters after I sig-fig it down to 3 significant digits. Okay, so there's my answer. Okay, when the first ball, the free fall ball, reaches the exact same height, my second ball, the constant velocity ball, will have traveled 20 meters. So here's another problem. Okay, Karen is playing soccer. She kicks a ball at an angle of 30 degrees on level ground at a speed of 18.4 meters per second. How far does the ball travel horizontally before landing, and how long does it take for the ball to land? Okay, so in other words, okay, if I'm to convert this, okay, into a 2 one-dimensional problems, I have a constant speed problem that moves horizontally and a free fall problem that moves vertically. Okay, so ball A moves horizontally at a constant speed of something. Ball B is thrown upwards at a speed of something. I want you at home to figure out what those values for the horizontal constant speed and what the initial speed for ball B is going to be. Okay, and then the questions get converted into where is ball A when ball B returns to its exact same height? And part B is how much time does it actually take ball B to return to its exact same height? Okay, I want you to solve those at home and bring them into class tomorrow. Thank you.